So next we're switching away from metric spaces and we talk about differentiation. So if we have a function on R, say, and then we say that that f is differentiable at x0 if the limit here, f of x minus f of x0, divided by x minus x0, if this limit here exists, as x go to x0. This quotient here is usually called the difference quotient. And it's always, of course, when you form this difference quotient, it's always assumed, obviously, that x is not equal to x0, so that the denominator makes sense, right? So if this limit here as x go to x0, if this exists, then we say that the function f is differentiable at x0, and the limit is called the derivative of f at x0, and this is how it's denoted. Okay? So now, the simplest possible example of this would be that suppose that you're looking at a function that is constant, so f is equal to f for some constant. C. Then if you're looking at this difference quotient, so f of x minus f of x0, x minus x0, well, the value at any point is c. So this here is c minus c divided by x minus y, x0. And so the denominator is 0, so this whole thing is 0. And so, of course, the limit, this is 0 for each x, and also each x0. So in particular, of course, the limit here exists. So the limit here of the difference quotient exists. And it's equal to 0, right? Because it's 0 for all x, for a given x0. So that would be like the simplest possible example. The second most simple example would be that you're looking at a linear function. So let's say that f of x is equal to x. Right? In this case, the difference quotient, so the difference quotient here, well, this here is x, this here is x0. So this here is for each x and x0, this is 1. So the limit, of course, in this case also exists. The limit here exists, and it's equal to 1. Right, so in this case, f is differentiable. At all points, and the derivative at all points is equal to 0. In this case, f here is also differentiable. And the derivative at all points is equal to 1. Okay, so now in general, how do we compute the derivative of a function? how do we compute the derivative? And for that, there are some basic laws how to compute it. So there's these laws. The sum rule, what's usually called the Leibniz rule. The quotient rule. And then also the chain rule. Okay. Now let me look at the first three rules first. So I have two functions, f and g. They are defined, say, on R, but it could have been a subset of R. And I'm assuming that they're both, right, actually we'll need one, okay, so both f and g are differentiable. At x0. Then we have the following, so we have the following lemma. One is we have that, so one, and this is really the sum rule. We have that the sum here, f plus g, so the sum of these two functions, this is the function that is just in x, it's just the sum of f of x and g of x. We have that this function here, f plus g, is differentiable at x0, and the derivative f plus g, the derivative of this at x0 is just the sum of the derivative. Okay. Let me prove this one here right away. So let's prove this. So we have the sum. So we are going to look at, so we form the difference, so form the difference quotient. So f plus g at x minus f plus g at x0, x minus x0. Right, so now what is this? So this here is, this is just f of x plus g of x minus, and then f of x0 plus g of x0. And then divided by x minus x0. Right? And so then you can split this up into two. You can write this difference quotient as if you split it up, if you collect the f's in the denominator. So I just collect the f's. And then afterwards I collect and I put it on two different fractions, separate them out, and then I collect the g's. And now you see that because f was differentiable at x0, this thing here, as x go to x0, this here goes to f prime. So this here goes to f prime of x0. This is what this difference quotient here. And this difference quotient goes to g prime of 0. So you have that indeed it does converge, and this is what it converges to. Right? And so this proves that the sum of these two functions is also differentiable, and their derivative is the sum of the derivative. Okay. The next thing we will prove is Leibniz rule, but before that, I need to kind of step back, and I want to, so before proving, so the next, maybe I'll just state it, and then we'll go back, and we need something. The next is what's called Leibniz rule. So it's all, you could also call it a product rule, but it's really quite generally called the Leibniz rule. And so this is when you're looking at the products of these functions. So the product function is a function in x that is just the product of f of x and g of x. And Leibniz rule, it says the following. That if f and g are differentiable at x0, then the product of these two functions here is also differentiable at x0, and the derivative of the product is the derivative of the first function at x0 times the value of the second function at x0 plus the symmetric thing in f and g, which is the value of f at x0 times the derivative of g at x0. Right, so the product is differentiable at x0 also, and this is what the derivative is. And in the notes, I just copied a little bit of thing, just for fun, from Wikipedia about Leibniz. That was kind of an interesting figure and played an important role a long time ago. Okay, so before I want to prove this, let me step back and let me make an observation about what it means to be differentiable at a point. So this is the next lemma. So you have a function f on R into R, and you assume that f, so if f here is differentiable, at x0, then I claim that then f here is also continuous at x0. Right? Okay. So in other words, being differentiable is stronger than being continuous. In a minute, we will see an example of something that's continuous but not differentiable. And so, okay, so now let's try to prove that. So, right, so I'm assuming that it's differentiable. So this means that this difference quotient here, this here has a limit, and that limit is the derivative, right, as x go to x0. So this means that, that there exists delta greater than 0, such that if x here minus x0 is less than delta, right? Of course, I'm assuming that it's not equal to x0. If it is less than the difference to between x and x0 is less than delta, then this difference quotient here, then f of x minus f of x0, x minus x0, minus f prime of x0, this thing here have to be less than 1, right? I mean, this is just using that this limit exists, and I'm sort of using, in place of epsilon, I'm using 1, right? Okay. Now, so this means just multiplying over, and multiplying over, you get that f of x minus f of x0 minus f prime of x0. This thing here times, I'm multiplying both sides, so multiply both sides by x minus x0. This is a positive thing, right? So I'm multiplying both things by that. So then I get this thing here, x minus x0, and then I get strictly less than x minus x0, right? Because this here is strictly positive, right? Because x is not equal to x0. So I have that, and so I get that. So I just split it up. So I have that f of x minus f of x0 is now less than x minus x0 plus f prime of x0 times x minus x0. And this is just the triangle inequality that we have used many times, just on R. Right. And so now you see that that if you now and this here, of course, I can also write like this. Sorry, I can just factor this out, and I can write it as 1 plus f prime of x0, no, like this. Right. And so now if I want this thing here, so now you can, if you were to, right, so now you want to prove that f is continuous at x0, so you want this here to be less than some given epsilon, right? So given epsilon greater than 0, you let delta 1 be like the minimum of, if you set delta 1 to be the minimum of the delta that I already chose, so then I have this inequality, and then epsilon over 1 plus f prime of x0. Right. So if I make delta, if I choose delta like this, then I have this inequality. I fill in that, so now I'm assuming that this thing here is less than delta 1. So again, I have this inequality because it's less than delta. So then when I fill in here delta 1 for this, then I see that this thing here times this is less than epsilon. Right? This here holds when x minus x0 is less than delta 1. Right? Again, because if it's less than delta 1, it's less than delta. So I have this inequality. And then I can use that delta 1, since it is less than this. And then I get this inequality. Okay, so this proof, right? So this is really what we want to prove, right? We want to prove that if it's differentiable, then it's also continuous. And the continuity here, I proved it, with the, epsilon or delta that you really should prove it like. Okay. Now let's look at some examples. So this means that if a function is differentiable, then it's continuous. Let me give you an example of a function that is, so let me give you 3 examples. The first example is maybe the simplest one. So this is the function f of x that is equal to the absolute value of x. So f here is defined on R into R. And it's just the absolute value. And so the absolute value here, so we've seen before, so f here is continuous. It's continuous at all points, right? In particular, of course, at 0, right? But if you now form the difference quotient, right? Suppose that x here is bigger than 0. And now look at the difference quotient. So the difference quotient at x0 equal to 0, if you're looking at that difference quotient. And you first look at where x is positive. If x is positive, then f of x minus f of 0, x minus 0. This difference quotient here, if x is positive, then this thing here is just x. So this is x minus 0, x minus 0. So this here is 1, right? This difference quotient is 1. This is when x is positive. When x is negative, then f of x, if x is negative, then the absolute value is minus x, right? So the difference quotient here, f of x minus f of 0, which is 0, x minus 0. This here is just minus x divided by x. But this thing here is minus 1. So for all, if you're looking at the difference quotient, and that comes from looking at the derivative as 0, then when you approach 0 from the right, then the difference quotient is 1. When you approach it from the, and when you approach it from the left, then the difference quotient is minus 1. So it doesn't have a limit, right? It has a limit from the right, from the left, but it doesn't have a limit if you don't restrict where it's coming from. So this function here is not differentiable. Yeah?
So you define what it means for like a minimum function as x approaches.
So, okay, so this is, right, so we did this earlier in the class. So if you take, that the difference quotient here that this thing here is converging to some number, say a, right? This here means that for all epsilon greater than 0, there exists a delta greater than 0, such that if x minus x0 is less than delta, and again, x is assumed to be different from x0, if you have that, then this difference quotient here minus this A is supposed to be less than epsilon. And so that's this. Okay, and so you see again in this example that we just looked at, where in the example that we just looked at, where, so in the example where f of x was equal to the absolute value of fx, if you were graphing it, then this looks like this, right? And we saw that the difference quotient, when you approach it over here, the difference quotient was 1. When you approach it over here, the difference quotient is -1. So if you take any little interval around 0, then the difference quotient could be either -1 or 1, right? But even however small you make this little interval, it's not like that it converts to some number, because it is both, there are both cases where it's 1 and cases where it's -1. Okay, so that's like the first example. And again, of a function that is continuous, but it's not differentiable at 0. In this case, it was a 0. And maybe a little bit more interesting example along the same line is the following. So if I, so this is again a function on R into R, and I said f of x equal to x times sine of 1 over x. This here is not really defined at 0, so I need to define it also at 0. So when x is equal to 0, then I just set it equal to 0, and otherwise I set it equal to x times sine of 1 over x. Okay. And so the thing is that this function here, so f here is continuous. In particular, it's continuous at 0. It's continuous. It's actually continuous everywhere, but it's mostly interested in it at 0. The graph of this. So remember that sine function looks like this. That at 0, at pi, at 2 pi, at 3 pi, and so on, at all of these, right, at all integer multiples, also for the negative ones, at all integer multiple of pi, sine function vanishes. And in between here, it is at pi over 2, it achieves its maximum, which is 1. And so the function looks like this. So this here is 1. Right, that's how a sine function looks like. And so now if you're looking at sine of 1 over x, that's going to be a function as you're going down. So if you're looking at this here was sine of x. But if you're looking at sine of 1 over x, as x goes to 0, this here becomes very large. So this means that as you're going to 0, it goes very rapidly through these periods where it oscillates between -1 and 1. So the value here is -1. And so it will look like this, that it will again, if you're looking at, it will again fluctuate, but it will fluctuate much more rapidly. So if this here, say, was 1 over pi, at 1 over pi, 1 over pi is the same as pi, there it would be 0, and it would like fluctuate. It would fluctuate, so it would look like something like this, but it would fluctuate. You know, and then as you're going away, it will fluctuate less often. Right? So as you're going down towards 0, it will fluctuate a lot. Right? It always, because sine always is between -1 and 1, the value here will always be between -1 and 1. But as you're going towards 0 from the right or from the left, it's going to fluctuate more and more. Right? As you're going away from 0, it's fluctuating less and less. Okay, so this is the function I'm interested in, and so, but when you multiply through by x, then you see when you multiply through by x, it's fluctuating, but it's always fluctuating between -1 and 1. If you multiply it by x, then as you're going to 0, this here will squeeze down, and it will become, the fluctuation will be 0, at 0. So it's easy to see that this function here is indeed continuous. But let's look at the difference quotient. So the difference quotient. So if we're looking at the difference quotient, so we're looking at, and we just look at the difference quotient at 0. So this here is the difference quotient. And so it's x sine 1 over x. The value at 0 by definition was 0. And so you see that now this here, the x, this here becomes just x sine 1 over x divided by x. And so you see that this here cancels with that. So you just get sine 1 over x. And so you see that now as x goes to, so when x here goes to 0, this here fluctuates, this here fluctuates between -1 and 1 and 1. But it doesn't have a limit, right? Because it's fluctuated wider and wider, right? So this is an example again. This is another example of a function that is continuous at 0, but not differentiable at 0. It's actually much worse than the previous. The previous one, the previous example that was this example is much more tame. It is not differentiable at 0. But if you were restricted to just positive things, then it would be differentiable, right? If you could also define derivative. So in general, when we define derivative, we let it be defined in a neighborhood of that point, so on either side. But if you were considering where you were allowing the function just to be defined at this point and then to the right, say, or to the left, then this function would be differentiable, right? But in this example here, it doesn't matter if you restrict the interval to just to the right or to the left, it's still not differentiable. Okay. Right, and so this example is something about that it fluctuates wildly, and that is causing it not to be differentiable. If it wasn't, again, if you defined it, if you didn't have this kind of, the x here is sort of serving as some sort of, it's dampening how much it's fluctuating, right? So if there wasn't an x here, then this function it would just fluctuate, and it wouldn't even be continuous at x0, right? But once I put this x on, then it becomes continuous. If I put another x, so if I'm looking at f of x equal to x squared times sine 1 over x. Suppose I'm looking at this function. So now I have sort of dampened the fluctuation even more. And so if I again looking at the difference quotient, so I'm looking at this function, maybe I should be more careful. So again, at 0, I need to define it separately. So I define a function that is 0 at x equal to 0, and then it is x squared times sine 1 over x. Otherwise, if I'm looking at this function, then I claim that this function is in fact differentiable at x at 0. And so let's look at that. So again, I'm looking at the difference quotient. And the value at 0 is 0. So I have this. And so this here is now just x squared sine 1 over x. This thing here is then x. And so you see that this difference quotient is just this. But this here does convert to 0 as x goes to 0. Right? So this function is actually differentiable. Right? It fluctuates, but it's more mild the way it fluctuates. Okay. Now let me get back to the rules. So we proved one rule that was this sum rule. Then the second rule we're interested in is when we're looking at the Leibniz rule. So we're looking at the product of these two functions. And each function is assumed to be differentiable at x0. And then we claim that the product function is also differentiable at x0. And this is the formula for the derivative. Right? To prove this one here, I need this fact that we have now proved, that if it is differentiable, then it's also continuous at that point. Okay. So I'm going to use that fact. And so, and now, so let's prove of Leibniz rule. So we have these two functions. We're looking at f of x. We form the difference quotient. So this is the difference quotient, x minus x0. We do this trick that we've done a bunch of times before when we also looked at products. We had two sequences, and we looked at the sequence that was the product of these two. Right, so if you have, just a reminder, that, I mean, it's not like, but so remember that if you had a sequence an and a sequence bn, and you knew that an converts to a and bn converts to b, then the product here converts to a times b, right? So, and when we prove that, we use this little trick with that we are we're splitting the difference between this and this, right? And so I'm going to do exactly the same trick here. So I'm looking at this thing here, and so I write this thing here as f of x times g of x minus, and it doesn't really matter, you know, where you're inserting it. So this here is like splitting the difference, and then I have to add it again. So this is certainly the same. I'm just subtracting it and adding it right back. And now I split this into two. So I write this in here. So this fraction I split into two. And the first one, I take this one here together. So, and you can factor out a g of x. You can write it like this. F of x minus f of x0. X minus x0. Right, so this is just, right, I'm just here. I'm factoring out the g of x. And then I'm left with this. This is this. And this is keeping the denominator like that. This is this part here. And then I have the other part here. But there you see that the f of x0 is factoring out. And then I have g of x minus g of x0, x minus x0. Like that. But now you see that as x goes to x0, right? Well, g was continuous at x0, right? So this thing here, as x goes to x0, this thing here goes to g of x0, right? This one here. That was because g was continuous, because it was differentiable, so it was also continuous. This here goes to the derivative. And the second thing here is, this here is just constant. And this here goes to the derivative. Like that. Right, so what we have proven is, this here is as x goes to x0. So you see that we have proven that this difference quotient here for the product has a limit, and this is what the limit is, right? And so this means that the product is differentiable, and this here is the derivative, and that's exactly the Leibniz formula, okay, which was this over here, this formula here. Okay, the next thing is that we want to prove the next rule is like this quotient rule. So let me prove the quotient rule. So Leibniz, right? Leibniz and Newton was the one that was responsible for calculus. And so the next thing I want to prove is this quotient rule. And so again, you have these two functions, f and g. And they are differentiable. At x0. And I'm also assuming that g here at x0 is not equal to, let's just assume that g is not equal to 0 everywhere. Is never is different from 0 everywhere. And then the quotient will say that if you're looking at the quotient here, and you take the derivative of the, so it say that if you're looking at the quotient here, maybe I should, so the quotient will say that if you're looking at this thing here, this now makes sense because g does not vanish. This here is differentiable. At x0, and the derivative of this function at x0 is given by the following formula, that it is the derivative of f at x0 times g of x0 minus f at x0 times g prime at x0 divided by g squared, so g of x0 times itself. I'll write that as a square. This here again, this here is just g of x0 times g of x0. Okay. So now let's try to prove that. So we're looking at f of x, like this, at x minus, so this is the difference quotient, at x0 divided by x minus x0. Right, that's the difference quotient. And so written out, this is f of x, g of x minus f of x0 divided by g of x0, x minus x0. So let me put this on a fraction with a common denominator. So if I do that, then this thing here is, right, so then I'm multiplying by g of x0, both in the numerator and denominator here. So I'm getting f of x times g of x0. And then here I'm multiplying by g of x in both numerator and denominator. So I'm getting this thing here, g of x. And then it becomes x minus x0, and then g of x, g of x0, like that. And so now you can write this thing here as, right, and so now you do the same trick as before. I mean, I could have gotten away slightly easier with looking at a special case of this quotient rule where f was a constant function 1. So I could do that first, and then the general case I could then get from this special case together with the Leibniz rule. But I chose to, it's most often that one do it together anyway, but if you have to do it together, you have to use the same trick that we just did. So we're using that over here. So f of x, g of x0, minus, and then f of x0, g of x0, plus f of x0, g of x0, minus f of x0, g of x. So this is again where I'm subtracting in the denominator or something, and then I'm adding it back up immediately. So I have this. Like that. And so now, if you do that, then you see that, so now you can, and now you split it up again into two fractions. So we split it up. And so this thing here, but there you see that there's a g of x0 that factor out. So this is equal to g of x0, and then you have f of x minus f of x0, and then x minus x0, g of x, g of x0, like that. And for the second one, you see that there you there you also have something that's factored out. And this is f of x0. Like that. And you're getting g of x0 minus g of x over x minus x0, g of x, g of x0, like that. Right? And now, okay, so now I can make this looks nicer. I can, this one here, cancel with that. And so I can write this thing here as 1 over g of x, f of x minus f of x0 divided by x minus x0. So this takes care of this. Here I can, I will write it as, I will take this one here out, so I'll write it as f of x 0 g of x times g of x0. And then I'm left with this thing here. And what I don't love about this thing here is it's not quite the difference quotient because the order of these two is wrong. So I switch the order, but if I switch the order, then I have to pick up a minus sign. So I get minus here, and now it is g of x, g of x0, x minus x0, like that. Okay, and now you see that as x, so as x goes to x0, so now as x goes to x0, well, this one here, the function was differentiable, so it's also continuous, so this goes to 1 over g of x0. This one here just goes to the derivative at x0. This one here goes to, again, because the function is continuous, this goes to minus f of x0. And then it's what I wrote before as g squared, it's d of x0 times itself. And then this thing here goes to the derivative of x0 at 0. Right? And now I can, if I want to, I can rewrite this thing here. If I want to put it back on a common denominator, then I have to multiply in the numerator and denominator by g of x0. If I do this, I get f prime of x0, g of x0, and then I get g squared of x0 in the denominator, and then here it's just those two minus f of x0, g prime of x0. And so you see that this here is exactly this formula here, this quotient rule. Right? So this proves that if you take two functions, the one you have in the denominator, if that is non-vanishing, so you can form the quotient. And if each of these two functions is differentiable, then the quotient is also differentiable, and this is the formula for the derivative. All right, so now why is this already really, really useful? So, we calculated, we calculated, so we started with the example of where f is a constant, right? And we saw that it's differentiable and the derivative is 0. Then the second example we had was where the function was x, and we saw that it was differentiable and the derivative is 1. Right? If you now take ax times right, so let's just take ax as the next example. This is like a constant function times this function. So Leibniz rule, sorry, if f of x is equal to a times x, where a is a constant, Leibniz rule say that the product of two differentiable functions is differentiable, and the derivative of this is the derivative of that, but the derivative of that is a constant function, so that's 0, so I don't even have to think about that. So it's just a times the derivative of the second function, but that's 1. So this here is the derivative of that. Right, so, and the next example would be that you're looking at ax plus, say, b. F of x is equal to this. Then you can use the sum plus, we know what each of these is. So you get that this one here is also differentiable, and the derivative of this function here is also just a. And you can continue like this, that if you take, if you now have a polynomial, suppose you take a to the power n. So if f of x is x to the power n, then you can think about this thing here as x times x times x times x, and you can use the Leibniz rule, right? And so if you use the Leibniz rule, so you just do it first in the case where f of x is equal to x squared. You can think about this as x times x. These are two differentiable functions. So the derivative here is now the derivative of this. So that's 1 times the other function, plus you keep this one here, and you take the derivative of that. So this is this. So this is 2 times x. Right? And so if you take this function here, using Leibniz rule, in this case, the derivative, it's differentiable, and the derivative is n times x to the power n minus 1. Right? So that's so and in fact, right, even more generally, just using the sum and the Leibniz rule, if you take any polynomial, a n x n plus a n minus 1 x n minus 1 down to the last thing is being a constant. If you take a polynomial like this, just using the Leibniz rule and the sum rule, using those repeatedly, we know that this here is differentiable, and the derivative is just like the sum of the derivative of these. So this is going to be n times x to the power n minus 1 plus n minus 1 times n minus 1 x n minus 2. And then this one here, the derivative is 0. So the last one you're getting something non-trivial for is a1. Right, so this is just using sum and Leibniz rule. Right? And so this is just using the sum plus Leibniz rule. Repeatedly. Okay. Now, likewise, if you take a rational function, so meaning that if you take something, if f of x is equal to some polynomial, a polynomial, so let's call it p of x divided by q of x. So where this here is a polynomial, and so is that. Right? So now you can use the quotient rule. Right? So the quotient rule will tell you that as long as you are looking at point where this here does not vanish, so then the quotient here is also differentiable, and it gives you a formula for the derivative in terms of the derivative of each of these two. And each of those two, they can be calculated like that. Right? So you see, it's already now we have like quite the derivative of a lot of functions, right? We have of all functions and of all rational functions. Rational functions, again, are quotients of a polynomial by other polynomial. Okay. So now the next rule that we want to talk about is the chain rule. So what is the chain rule? So the chain rule is a little bit different from those three rules here. And it is where you take the composition of functions. So the next is the chain rule. And again, this is about composition of functions. Okay, so I have a function f that goes, say that it goes from some interval a to b into another interval from c to d. And then I have a function g that goes from this interval here into R. Because g is defined, you know, like whatever the image of f, always if it's in the set, this is where g is defined. Then you have that you can form, if you take some x in here, so if x here is in a to b, then this here makes sense. And this is now an element here, so this is where g is defined, so this here makes sense. Right? And this is now what we call the composition, and we write it like this. It's important to write it in the correct order. And so this is the composition function. Okay, and the thing is that this, so now the chain rule is the following. So the chain rule is the following theorem. That if f is differentiable, at x0 and g is differentiable at y0, where y0 is equal to the value of f at x0, then the composition of these two functions is differentiable at x0, and the derivative is equal to the derivative of g at y0 times the derivative of f at x0. So this is the chain rule. Right? The chain rule says that the composition is also differentiable at x0, and this is the formula for the derivative. Okay, let's try to prove that. And so that in this case, it's useful to divide up to two cases. And the two cases to divide up to, so let me just look at the special case first, and then once we understand that, it would be clear, the general case would be clear. So let's make one assumption. So let's try to prove it. But we assume first that the derivative, I'm going to assume that the derivative at x0 is not equal to 0. So I'm assuming that first. What does this guarantee me? Well, remember that the derivative is the limit of this difference quotient. Right, so this is the limit. If this here is not equal to 0, this means that when x is very close to x0, this thing here is very close to this thing that is not equal to 0. But then it means that if you are very close to x0, f of x cannot be equal to. So if you have this here, this implies that f of x is not equal to x0 is not equal to f of x0 for x sufficiently close to x0. I'm always assuming, of course, that x is not, but x is not equal to x0. Right? So I'm going to first make this assumption. And if I make this assumption, what I get out of it is that this thing here is not equal to that. Why is this useful? Because now I can actually look at this difference and I can divide by it. Okay. So I'm going to just to make things a little bit clearer. So I have my function. So this here is f, and here I have g. Here I have x0, but under f it's taken to this, which is f of x0, but this I also will denote by y0. Right? So I'm denoting, just to make things clearer, y0 is just the value here. And then I will use f of x, I will denote by y. Okay. So now I'm looking at the difference quotient. So I'm looking at I'm looking at g of f of x minus g of f of x0. X minus x0. That's what I'm supposed to look at. And I can write this thing here as g of y, because this here I also call y, right? So you can write it like this, g of y0. And then I will write it as y minus y0, but I didn't have this in the denominator up here, so I have to multiply it back on. And then I still have to divide by like that. Right? So I can write it like this. This here I'm happy with. We'll get to this in just a second, but I'm happy with this expression. The other one, I really want to put it back in terms of f. So I'm writing this thing here. And this thing here, I really want to put it back in terms of f. So if I do that, I write it as f of x minus f of x0. X minus x0. But now you see that as x go to x0, right? Well, as x go to x0, because the function f was continuous at x0, it means that if x go to x0, then the value at x, which is y, will go to the value at x0. So when x goes to x0, we have that y goes to y0. Right? So this means that this thing here, this here converge. Right? That's just because the function f is differentiable. So this here will converge to the derivative. So this, the second factor here is converging to f prime at x0. The first factor is, but now you see that we just argued that y goes to y0. So this is also a difference quotient, but it's a difference quotient for g. And since y goes to y0, this difference quotient here goes to the derivative of g at y0. But that's exactly the formula that we wanted to prove, except that we made one assumption, that the derivative of f at x0 was not equal to 0. We made that assumption only so that this number here was not equal to 0, right? And so we could kind of divide by it, right? But actually, otherwise, right? If you, for some reason, if y was not equal to y0, but right, then this formula here would still hold, right? So it's only the possibility that that y could be equal to y0. But now you see that if you were just looking at the difference quotient, g of y minus, g of f of x minus, so this is the difference quotient that is the one we really have to look at for the composition, right? And this is what we also called, this here is what we call, this thing here is what we called y0, this thing here is what we call y. And the only case we haven't dealt with is where f prime of 0 is equal to 0 and y is equal to y0, right? This here again was f of x, and this here was equal to f of x0. So this only this case here we haven't dealt with, right? But you see that if it so happened that f of x was equal to f of 0, then this difference quotient here, the denominator would trivially be 0, right? And so you want to prove, we have that if this here was not equal to 0, then we have that this is converging to the derivative. And the only case we have to look at where this derivative is 0, so we are claiming that. So the only case we're left with that we haven't dealt with is, first of all, where the derivative, so let's see, so let me just write down here clearly. The remaining case for the chain rule so the remaining case is that the derivative at x0 is 0, right? And we have already observed that if the derivative is 0, but y is not equal to y0, if this is the case, then actually g of f of x minus g of f of x0, this thing here still converge. In this case here, where this is the case, this here still converges to 0, right? So we still have the chain rule in that case if this here was not the case. The only thing we have to worry about is what if y was equal to y0? But if y was equal to y0, when we're looking at the difference quotient, this is the difference quotient after all. And so in that case, this thing here is y0, this is y0. But in that case, the difference quotient is actually 0 already. So of course, it's going to be very close to 0, right? It actually is 0, right? So you see that the remaining case, that's sort of trivial. Right? But we wanted to first exclude it because we wanted to be able to divide by this difference, right? And then once we have seen that under that assumption, it was, we got the formula we wanted, then we go back and then we say that not only you know, the remaining issue was, well, first of all, was the case where the derivative was 0, but in fact, the only case that was potentially a problem was when y was equal to y0, but for that, the difference quotient was actually trivially 0. Okay, so that's the chain rule. And so we only have a few minutes left, and I won't quite be able to get through all of the stuff, but I can get through one more lemma. And then I'll pick up from here next time. The notes are already posted, but so the last bit of the notes we'll do next time. So the following lemma here. So if you have a function, say from R to R, and you have that x here, x0 is a local max or min. So f is a function from R to R that is differentiable. And x0 is a local max or local min for f. Then the derivative at x0 is equal to 0. Okay. Let me remind you what a local max and local min is. So if you take a function, so a local max, similarly for a local min, if you have a function here, you have here x0, a local max means that in a neighborhood of this point, then the value at x0 is the maximum. So local max at x0 means that there exist delta greater than 0 such that that if you're looking at the interval to either side of x0, this interval, and you're looking at f here restricted to this subset, then x0 is a local max, is a max. So this means that f of x0 is equal to the max of f, where x here is in this little interval here. Oops, like that. Right. So it's it may not be right. So so the idea is that it's just the function may look like this, and this here is x0. So you see that in a neighborhood like this, it looks like that you have that this x0 is a maximum, but there might even be somewhere else where the value is much higher. Right? So that's a local maximum, and similarly for a local minimum. Okay, and so I won't be able to actually prove this lemma. We'll prove that next time. And then once we have that lemma, we prove what's called Rolle's theorem, and then we will use it to prove the mean value theorem. But I'll do that next time. But it's actually in the notes that I posted already.